Hello, in this video, we will show how to generate random numbers and number combinations in R. So we will go to RStudio, and you can also use this source file if you want to download from this website's download menu. You can find R tutorials download link. Then we go to RStudio and find this file and go to the section for generating random numbers and combinations. So first we will use a function called combn, C-O-M-B-N, combn for generating all combinations from n items and taking k at a time. So say we have a vector from 2 to 5. So items is 2 to 5. So we show items 2, 3, 4, 5, these 4 elements vector. Then we choose k equals 2. Then we can use combine n items k. Then we show the result. The result is like a matrix. So each column is 2 elements. Then this matrix will contain all combinations of 2 elements from 2 to 5. So each time we choose 2 from these 4 elements. So 2, 3, 2, 4, 2, 5, and 3, 4, 3, 5, 4, 5, and so on. So there are total 6 different combinations. And you can also choose the particular element. For example, we choose say 2, 3, 5. Then you can also use this function for string. For example, we will choose all 3 combinations from these 5 string, T1, T2, T3, T4, T5. So this is a matrix, and each column includes combinations with 3 elements from this total 5. And this matrix lists all combinations. Then next we show the functions for generating random numbers, and the random numbers associated with statistics distributions. So first we will use uniform distribution. So R uniform. Then this means we'll generate random numbers from a uniform distribution with between 0 and 1. So for example, we choose 10 such random numbers. So uniform random distribution are continuous. So each number is continuous number between 0 and 1. You can also choose, for example, 10 numbers between 15 and 50. So we just set a minimum 15 and a maximum 50. So these 10 numbers are generated. You can also calculate the mean of these random numbers. Here we choose 1000. So you can see the mean is about 32. If we look at this, plus this together, divided by 2 is 32.5, right? So very close to the mean. Then you can use the rnorm to generate random numbers from a standard normal distribution. So which means mean is 0 and standard deviation is 1. So rnorm 10. So 10 numbers are generated with 0 mean and standard deviation 1. For example, you can also calculate this random 10,000 such random variables. You can see the mean is very close to 0 and standard deviation very close to 1. Of course, you can also choose the mean and standard deviation in this function. So here we choose 10 such random variables from normal distribution with mean equals 100 and standard deviation equals 15. So we just verify its mean value 100 and standard deviation for very close to 15, right? So next is the binomial. So in the binomial distribution comes from the Bernoulli process, which is trying with the success rate, or we say the probability here, for example, 0.3 with the success rate, and we take a number of experiments and then count how many times the positive success. So for example, here we can calculate one such random variate from binomial distribution with 10 Bernoulli trials and success rate 3. So we choose only one random number from these experiments. So what means this? This means if we take Bernoulli trials 10 times and each time has success rate 0.3 probability, then how many success numbers in this trial? So because we only choose one, so we will see this number is a discrete random variate. So we run, so 3. So for example, this trying, we get 3 positive or 3 events occurred, right? Because we had take 10 trials. And for example, we will choose 10 such random variates with 10 trials and success rate 3 in each trial. So you can see 10 discrete numbers between 1 and 4 or 5 occurred. And we can also, for example, calculate the mean value of a binomial distribution. So here we choose 100 such random variates and with the success rate 0.3 from 10 trials. So you can see the mean is about 2.83. Actually, binomial distribution's mean value is trying number multiplied with the success rate. So here the mean value is 3. So you can see very close to 3. So next we will show a Poisson random variate. So Poisson experiment is, I would say the Poisson process is to count how many discrete events occurring during a specific time interval. So for example, we have a lambda, a success rate 10 here. So this means the 10 means in a unit time interval. For example, in 1 hour, there are in average coming 10 telephone calls. And now we will try different 10 times. Then can count how many telephone calls coming in each time, each 1 hour, right? So here we will use R Poisson 10, then lambda 10. So you can see the result is discrete and numbers all around 10, 9, 13, but very they come around the 10. So because the mean value of a lambda distribution is equal to this lambda, mean value of a Poisson distribution equals this lambda. So lambda we call lambda is access rate, occurring rate. Then we can calculate the mean for Poisson distribution with 100, 1000 random variates and with a success rate 10 or occurring rate 10 in a time interval. So the result is very close to 10. Then we will see how to use exponential distribution random variate. So rexp will generate 10 random numbers from exponential distribution with a success rate 0.1. So exponential distribution is a continuous distribution which model the random time until next occurring of the event. And here we have a parameter called the rate. This rate is actually the same as a lambda in Poisson. So exponential also associated with a Poisson process because we have a success rate in a time interval, but different difference between exponential and Poisson is that exponential is a continuous random distribution, and we want to calculate the time until next event come. Not count how many times occurring. We just want to know the time between next occurring of the event. But the event is the same in the Poisson process. So here we say rate is 0.1. This means in average 1 hour, there are only 0.1 occurring. So this means that 10 hour only 1 occurring of the event. Then we will get the random numbers for time until next event occur. So we can use r exponential 10 for 10 such numbers and with rate 0.1. So these 10 numbers means the time until next event occurring from this exponential distribution. So here you can see the time is little over 1 hour, about 1.3 hour, and 0.7 hour, and about 100 hour until next event occurring, and 39 hour like this. So this is continuous. But if you want to calculate the mean, how it's going, for example, we generate 1,000 such exponential distributions, random varied, and with the rate 0.1, we calculate the mean. Mean is about 10.28. So you can see the exponential distribution's mean is actually the reciprocal of this rate. So because in 1 hour average only 0.1 occurring of the event, this is the same to say that average time until next event occurring is 10 hours, right? We get the mean very close to 10 hours. Thanks for watching.